Welcome to my talk at QCrypt 2021. My name is Andreas Bluhm. I'm a postdoc at the University of Copenhagen, and my talk is called Position-Based Cryptography, Single-Qubit Protocols Secure Against Multi-Qubit Attacks. And this is joint work with Matthias Christandl and Florian Speelman. So imagine the following situation. You come with a lot of money to a bank, and you give that money to the person behind the counter. So the question is, why do you do that? Because in principle, you don't know that person. So why do you trust her? And the answer is you trust the person behind the counter because of her location, because you assume that everybody who is behind a bank counter is probably a clerk working at the bank. So that's why she's trustworthy. And that is the same idea as the idea behind position-based cryptography, because there you want to use the position of a party as a credential instead of, say, a secret key. So how can classical protocols for this position verification task look like? Well, we consider only the position in 1D for simplicity. So here you actually have a line. And on this line, there are two verifiers, V0 and V1. And they want to verify that a prover P is at position Z, say halfway between them. Doesn't really matter. And the way they can do this is, or they can try to do this, is shown below, where here you have a time going downwards and position going to the right. And so the V0 can send a classical string X of length n to the position Z. V1 does the same with a string Y of length n, such that X and Y arrive at the same time. Then the honest prover should compute a function that they have agreed upon before, f of X and Y, and send back the result to both V0 and V1. And if she answers fast enough, consistent with special relativity, the verifiers will accept if the bit that they receive is correct. Why does that not work? Well, imagine now that there is no honest prover at Z, but there are two adversaries, Alice and Bob, and they are to the left and to the right of Z, but not at Z. Otherwise, this wouldn't make sense. Well, the diagram is as before, but now V0 sends X, V1 sends Y, and Alice intercepts X and makes a copy of this classical bit string. So she sends on X to Bob and keeps a copy of X for herself. And Bob does the same thing with Y. As soon as Alice receives Y from Bob, she will compute the function f, x, and y and send it to V0. And Bob will do the same thing on his side and send it to V1. As you can see from the diagram, from the point of view of the verifiers, this looks exactly like the situation before. So they will not be able to tell the honest prover from adversaries Alice and Bob. So we have seen that in the classical case, position verification cannot be done. So since we're at QCrypt here, how is quantum going to help here? Well, as you've noticed, the key step in the attack that we have just seen is that Alice and Bob have to copy their bit strings X and Y. And by the cloning theorem, quantum information cannot be copied, at least not perfectly. So as you all know, in other words, there's no quantum channel such that rho gets mapped to rho tensor rho for all quantum states rho. On the downside, now that we are considering the quantum setup, also the quantum attackers are more powerful because now they can also use quantum communication. In particular, they can use entanglement for quantum teleportation, for example, and this gives them the possibility to break any position-based any position verification protocol. So it has been shown that unconditional security is impossible, but we still have hope that we can prove that attackers actually need a lot of entanglement to attack such protocols. This would mean that position verification protocols are practically secure. So let us now consider the single-qubit protocol, which is the protagonist of this talk. And the first variant we're going to consider is the qubit routing protocol. And the situation, 1D situation, looks like before. But now V0 and V1, the verifiers, do not only send classical bit strings X and Y, but V0 also sends a qubit Q to the prover P. And then depending on the outcome of F evaluated at X and Y, the prover P has to send the qubit back to V0 if the function is 0, and on to V1 if the function is 1. And then the verifiers will check whether the qubit they got from the prover is the correct one and accept if it is. So let's give a bit more details here. We didn't come up with the protocol, but the protocol goes back to work by Kent et al. In 2011. We just analyzed its security. And the verifiers will prepare the qubit Q in the states 0 or 1 in the computational basis, or plus and minus with equal probability at random. And at the end of the protocol, they will measure either in the computational basis if the one that they send was 0 or 1, or in the Hadamard basis if Q was either plus or minus, and if the outcome that they get and if the qubit arrives at the right time, they will accept. So how could attacks on this protocol look like? Now we again consider a party Alice and a party Bob, and each party has 3 registers, A tilde, and AC, and B, C, B tilde, and B. So let's look at Alice's registers. So she has a qubit register A. She has a local register A tilde, which can be more qubits, and she has some qubits AC that she will communicate later, and the same for Bob. So as soon as she intercepts the qubit, she will store it in A, and depending on the bit string X that she has intercepted, she will apply a unitary X to her systems, and Bob will apply a unitary VY to his systems. Then by the constraints imposed by special relativity, they have 1 round of communication. So Alice will always send her string X to Bob, and Bob will send his string Y to Alice. And Alice will send her system AC to Bob, and Bob will send his quantum system BC to Alice. So after that round of communication, Alice can again apply a unitary to the system she controls, which is K of X and Y. And Bob can use now L, also depending on X and Y, because now he has both bit strings. So now we have seen what the most general attacks on the qubit routing protocol look like, and thus we are ready to state our main results. So let us assume that there's at least 10 classical bits, and let us assume that the verifiers choose the bit strings X and Y that they send, which have length n, uniformly at random. Then there exists the classical Boolean function on 2n bits, with the property that if the number Q of qubits each of the attackers Alice and Bob controls satisfies that Q is at most 1/2 n minus 5, then the attackers are caught with probability at least 2%. Moreover, a uniformly random function f will have this property, except with exponentially small probability. So that means we cannot give you a concrete function f for which the protocol is secure with these parameters, but we can say that a uniformly random function f will make the protocol secure with very high probability. We will talk about concrete functions later in the talk. 2% detection probability doesn't sound like a lot, but we can make this larger by sequentially repeating it. So that means that the success probability of the attackers can be suppressed exponentially by sequential repetition, and we can make that success probability of the attackers as small as we like. So let's go now through the proof idea of this. And the qubit routing was already considered in this work by Bluhm et al. In 2013. But security was only investigated for perfect attacks. So attacks where the Alice and Bob have to succeed perfectly. And now in our paper somehow makes the proof strategy they use robust and completes the proof in a sense. So how we do this is that we will consider an equivalent protocol, namely an entangled protocol, which is fairly standard. So it's equivalent to a protocol that verifiers send half of an entangled pair instead of like just a single qubit, which is random. So the first observation, which is already present in this work by Bluhm et al., is if you consider a state psi0, from which a qubit can be recovered at V0 by acting on Alice's systems, and in a state psi1, where the qubit can be recovered from acting on Bob's systems at V1, then the overlap of these 2 states cannot be too large. So this means that the states have to be quite different. And if you think about it, this implies that the action of the attackers before actually communicating already determines where the qubit ends up. So they have to decide before actually being able to talk to each other, which sounds like there's some security that you can prove here. So now we can discretize the possible quantum strategies that the attackers might adopt with the help of epsilon nets. And we can also construct classical rounding functions which capture the essentials of the quantum strategies that the attackers might use, which we then call epsilon Q classical roundings. I will not go into details here. But what do I mean by capturing the essentials? That means that these classical roundings will give rise to a Boolean function for each attack Alice and Bob can come up with, controlling at most qubit each. And this Boolean function will agree with the Boolean function f used in the routing protocol on all pairs of classical bit strings x and y on which the attackers succeed with probability at least 1 minus epsilon squared. So almost surely. Almost surely. Well, and now we can complete the proof using these epsilon Q classical roundings. Namely, we can do a counting argument. So we compare the number of epsilon Q classical roundings if epsilon Q are not too large to the number of Boolean functions f on 2n bits. And we find that the latter are far more than the former. So that means for Q at most n½ minus 5, most Boolean functions are far from any functions produced from classical roundings. This is why a random function will do. And going back to translating it back into success of the protocol, we find that for if Q is at most n½ minus 5, Alice and Bob cannot succeed with probability at least 1 minus epsilon squared on too many input pairs x and y. So they will make quite a lot of mistakes. And this was why, in the end, the protocol is secure. So that was the idea of the proof. And there's a second version of the protocol that we can consider. And it looks almost like the one we had before in the upper part. But now, instead of routing a qubit, the prover has to measure something. And she has to send back a bit B to both V0 and V1. And this protocol resembles more the ones considered in this work by Wege and König from 2011, which is also looks like a BP84 type protocol. And what the verifiers do is they prepare the qubit Q randomly as either 0 or 1, and then apply a Hadamard gate if the function value is 1. So then it's either plus or minus the qubit. And the prover measures upon receival of the qubit Q and the classical strings, the prover measures in the basis specified by the function value and sends back the outcome that she got to the verifiers. And then the verifiers check whether B arrives at the right time and is consistent with the state that they actually sent. So why have we considered this protocol? Well, we consider this protocol because it's close to the one used in the Wege and König article, but they use n qubits, whereas we use a single qubit, but we also use a Boolean function on 2n bits, which they don't use. So we can actually prove that using an atropic uncertainty relation and modifying the proof that we have seen slightly, we can prove that the same security as for the routing protocol holds for the measuring protocol. But the routing protocol is simpler in the sense that the prover does not need to measure. So why do we consider it? Well, the advantage is that the security proof for the measuring protocol still holds if quantum information travels slowly. So only the classical information has to travel at the speed of light. And that's realistic given the current technology, because there are usually qubits are transmitted using fiber optics, and they are slower than the speed of light. Well, now we can ask about noise robustness. And hitherto we have assumed that the honest prover always succeeds perfectly. So now what if she only succeeds with probability at least 99%? It doesn't matter which protocol we consider. So we can repeat the protocol independently r times and accept if the final measurements accept more than roughly r times, because delta is a small constant. So then we can prove the following theorem. So assume that a function f on 2n bits is chosen uniformly at random. Then an honest prover succeeds in the protocol with noise level at most 1% with probability at least 1 minus c to the r, where r is a constant smaller than 1. And if the attackers control at most q qubits at the beginning of each round, and q is at most 1/2 n minus 5, they will succeed at probability at most c prime to the r, where also c prime is strictly smaller than 1. And repeating r times and making r as large as you need, you can make this probabilities high for the honest prover and low for the attackers. And so the protocols are still secure if you consider a small amount of noise. How do you prove this? Well, you can use a Chernoff bound to prove it. So we have talked about uniformly random functions which make our protocols work, but what about concrete functions? And let's consider the binary inner product function. So that's the usual inner product. You just consider it mod 2. And there we can prove basically under the same assumptions as before. So uniformly random bit strings x and y. And the number of qubits now has to be at most 1/2 of logarithm of n minus 5. Then the attackers are caught during the routing or measuring protocol, depending on what you use, with probability at least 2%. So we can see that the bounds here are exponentially worse than the one we have for random functions, but security still holds in the same way. And the proof is based on communication complexity of the function that we look at. So let's conclude with an outlook. So what's the ultimate goal in this position verification protocols? Well, as we have said in the beginning, one would like to prove that the attackers need an exponential amount of entanglement to break some of the position-based verification protocol. And in our case, we can show that the honest prover only manipulates 1 qubit, whereas the attackers need at least order of n qubits. And that's not only exponentially more resources, but it's actually unboundedly many more. And this still holds for concrete functions where, okay, now the attackers only need order of log n qubits, but still it's unboundedly many more than the honest party needs. So where's the catch? Why does that not already show everything we could wish for? Why haven't we solved our problem? Well, you have to be careful what you compare here, because the honest prover actually needs to manipulate order of n classical bits. So if you compare all the resources the honest prover needs and all the resources the attackers need, then the trade-off between the two is only linear, not exponential, what you would like, and it definitely not unbounded. So we haven't succeeded in everything we wanted, but still the protocols are fairly nice, because now we can conclude that the routing and measuring protocols have some very nice features. So the honest prover, as I've already pointed out, only needs to handle 1 qubit and needs not to even measure it, at least not in the routing protocol. And the verifiers need not create entangled states or have quantum memory. And we have seen that the more classical bits the verifiers send, the more qubits the attackers need, which is the nicest feature about this protocol and the two variants. But the honest prover does not need more quantum resources. So this leads us to the main takeaway of this talk, which is that we can spend classical resources to increase the quantum cost of the attackers without increasing the quantum cost of the prover. So there's a certain trade-off of classical resources on the honest side and quantum resources at the attacker side. With that, these are the references that have appeared during the talk. I would like to thank you for listening and well, look forward to any questions that you might have. Thank you very much.